Mordenite is an industrially important zeolite. It has 12 ring main channels with the dimensions as shown here, 6.5 angstroms and 7 angstrom here. And these main channels are connected to 8 ring side pockets with dimensions as indicated here. Mordenite is used as catalyst and has adsorbents in separation applications. Due to its high thermal and acid stability, it is effective as a catalyst for reactions that take place at high temperatures, such as hydrocracking, hydroisomerization, alkylation, dewaxing, and for the production of dimethylamines. For further structural information, I refer you to my paper in ACS-Omega 2020. Talu and Zwiebel published a set of experimental data on the adsorption of mixtures of carbon dioxide and propane in the Mordenite zeolite. Well, for low concentrations of CO2 in the bulk gas phase mixture, the mixture adsorption equilibrium favors CO2. However, as the mole fraction of CO2 in the bulk gas phase mixture increases, the selectivity reverses in favor of propane. And the experimental data here plotted as the red circle shows selectivity reversal. At this point, we have azeotropic adsorption at a mole fraction of 0.6 for CO2 in the bulk gas phase mixture. In order to understand the selectivity reversal phenomena and the occurrence of azeotropic adsorption, we conducted configurational bias Monte Carlo simulations for mixture adsorption and Mordenite zeolite. These CBNC simulation data are published in my ACS-Omega paper in 2020. Watch also my videos on azeotropic adsorption and reversals of adsorption selectivity on my YouTube channel. The CBMC simulation data are shown here, and the data are in remarkable agreement, nearly quantitatively, with the experiments of Talu and Zwiebel. Let's understand why the experiments show selectivity reversals, as do the CBMC simulations, and why the IAST estimates indicated by the dashed lines are in extremely poor agreement with the experiments and with CBMC. Indeed, selectivity reversals are not anticipated by the IAST, and the IAST anticipates the selectivity to always favor carbon dioxide. In order to understand the failure of the IAST, we need to look further into the location of the gas adsorbates within the pore channel structure of Mordenite zeolite. The IAST for mixture adsorption equilibrium mandates a uniform distribution of gas adsorbates within the pore landscape. For adsorption of CO2 and alkane mixtures within Mordenite, we have segregated adsorption with carbon dioxide preferring to locate within the side pockets. And therefore, the alkanes are further removed from CO2 than would be the case if the adsorbates were uniformly distributed. This means that the competition faced by the alkanes with CO2 is lower than that anticipated by the I.Ch.E.J. In order to appreciate the segregation phenomena visually, let's have a look at animations showing the motion of CO2 and methane within the Mordenite zeolite. We see that the CO2 molecules are located in the side pockets and are virtually stagnant, whereas the methane molecules can traverse along the main 12-ring channels and are far removed from CO2. So configurational bias Monte Carlo simulations serve to demonstrate the phenomena of the segregated nature of mixture adsorption equilibrium and the failure of the ideal adsorbed solution theory. I now illustrate the importance of selectivity reversals on separations of mixtures of CO2 and propane in a fixed bed adsorber packed with Mordenite zeolite. I perform transient breakthrough simulations using CBMC simulation data of unary isotherms, and I show here two sets of simulations for two different compositions of the feed mixture. For a feed mixture with 50-50 proportions of CO2 and propane in the feed entering the fixed bed, the transient breakthrough simulations are performed with the RAST shown by the continuous solid lines. The red line indicates the breakthrough of CO2. The blue line indicates the breakthrough of propane. The corresponding simulations using the IAST are indicated by the dashed lines. Both IAST and RAST anticipate that CO2 breaks through at the end and propane breaks through earlier, as is the case in the adsorption data with varying CO2 in the bulk gas phase mixture. So we're looking at a composition somewhere here. Both RAST and IAST anticipate that the mixture adsorption is in favor of CO2. The x-axis used in the representing the breakthrough simulation is a modified time axis, where T is the time in seconds, Q naught is the flow rate of the feed mixture at the inlet in units of liters per second. M sub ADS is the mass of adsorbent, which is a Mordenite in the fixed bed adsorber in kilograms. So the x-axis is the units of liters per kilogram. The right-hand graph shows the simulations for a feed mixture with a mole fraction of 0.7 CO2 in the feed mixture. The RAST simulations are shown by the continuous solid lines, and we note that the component to break through first is CO2 because the adsorption is selective to propane. On the other hand, the IAST anticipates that the first component to break through is propane, and CO2 is the component that is less strongly adsorbed. So this is the consequence of thermodynamic non-idealities on separation in a fixed bed adsorber. The RAST correctly anticipates that the adsorption selectivity is in favor of propane, whereas the IAST anticipates the adsorption selectivity is in favor of CO2 for this mixture composition of 0.7. So ignore thermodynamic non-idealities at your own peril.